Eigenvalues and eigenvectors of matrices. Definitions. Definition 1. A non-zero vector capital X is an eigenvector or characteristic vector of a square matrix A if there exists a scalar lambda such that Ax equal to lambda x, then lambda is an eigenvalue or characteristic value of A. Note: the zero vector cannot be an eigenvector even though A into 0 equal to lambda into 0, but lambda equal to 0 can be an eigenvalue. Example: show X equal to the column matrix 2, 1 is an eigenvector for the matrix A, 2 by 2 matrix A equal to 2, minus 4, 3, minus 6. Solution of that matrix is, the problem is Ax equal to 2 minus 4 3 minus 6 into 2 1 is equal to 0 0. But for lambda equal to 0, lambda x value is 0 into 2 1, matrix 2 1 is equal to 0 0. Thus x is an eigenvector of A and lambda equal to 0 is an eigenvalue. Eigenvalues. Let capital X be an eigenvector of the matrix A, then there must exist an eigenvalue lambda such that Ax equal to lambda x or equivalently Ax minus lambda x equal to 0 or A minus lambda into x equal to 0. If we define a new matrix B equal to A minus lambda into A minus lambda I, then Bx equal to 0. If B has an inverse, then x equal to B inverse 0 equal to 0. But an eigenvector cannot be 0. Thus, it follows that x will be an eigenvector of A, and if and only if B does not have an inverse or equivalently determinant of B equal to 0 or determinant of A minus lambda equal to 0. This is called characteristic equation of A. Its roots determine the eigenvalues of A. The roots are called eigenvalues of A. Example of eigenvalues. Example 1. Find the eigenvalues of the matrix A, 2 by 2 matrix, that is 2 minus 12, 1 minus 5. Now determinant of lambda I minus A is equal to determinant of lambda minus 2, 12, minus 1, lambda plus 5 equal to lambda minus 2 into lambda plus 5 plus 12. Implies lambda square plus 3 lambda plus 2 equal to lambda plus 1 into lambda plus 2. Therefore, the two eigenvalues are minus 1, minus 2. Note: the roots of the characteristic equation can be repeated, that is lambda 1 equal to lambda 2 and so on lambda k. If that happens, the eigenvalues is said to be multiplicity of k. Example: find the eigenvalues of A equal to 2, 1, 0, 0, 2, 0, 0, 0, 2. Determinant of lambda I minus A equal to lambda determinant of lambda minus 2 minus 1, 0, 0 lambda minus 2, 0, 0, 0 lambda minus 2 is equal to lambda minus 2 whole cube equal to 0. Then lambda equal to 2 is an eigenvector of multiplicity 3. Next, eigenvectors. To each distinct eigenvalue of a matrix A, there will correspond at least one eigenvector which can be found by solving the appropriate set of homogeneous equations. If lambda is an eigenvalue, then the corresponding eigenvector xi is the solution of A minus lambda I into capital I into capital Xi equal to 0. Okay, example: lambda equal to minus 1. When lambda equal to minus 1 into I minus A is equal to the matrix minus 3, 12, minus 1, 4, implies 1 minus 4, 0, 0, where x1 minus 4x2 equal to 0, that implies x1 equal to 4t and x2 equal to t. Therefore, the eigenvector capital X1 equal to column matrix x1, x2, that is t into 4, 1, where t not equal to 0. When the eigenvalue lambda equal to minus 2, that is minus 2 into I minus A is equal to my matrix minus 4, 12, minus 1, 3, implies 1 minus 3, 0, 0. Therefore, the eigenvector, second eigenvector capital X2 is equal to a matrix column vector x1, x2 is equal to S into 3, 1, where S not equal to 0. Next example, find eigenvectors of 3 by 3 matrix A, that is first row 2, 1, 0, 0, 2, 0, 0, 0, 2. Recall that lambda equal to 2 is an eigenvector of multiplicity 3. Solve the homogeneous linear system represented by 2i minus a into x is equal to the matrix 0, minus 1, 0, 0, 0, 0, 0, 0, 0 into column matrix x1, x2, x3 is equal to 0, 0, 0. Let x1 equal to s, x3 equal to t. The eigenvectors of lambda equal to 2 are of the form capital X equal to x1, x2, x3. It is equal to s0t, or it is equal to s into 1, 0, 0 plus t into 0, 0, 1, where s and t not both 0. Next, properties of eigenvalues and eigenvectors. Definition. The trace of a matrix A designated by trace of A is the sum of the elements of the main diagonal. Property 1. The sum of the eigenvalues of matrix equal the trace of the matrix. Next, second property. A matrix is singular if and only if it has a 0 eigenvalue. Third property. The eigenvalues of an upper or lower triangular matrix are the elements on the main diagonal. Next, fourth property. If lambda is an eigenvalue of A, matrix A, and A is invertible, then 1 minus lambda is an eigenvalue of matrix A inverse. Next, fifth property. If lambda is an eigenvalue of A, then k into lambda is an eigenvalue of k into A, where k is any arbitrary scalar. Sixth property. If lambda is an eigenvalue of A, then lambda power k is an eigenvalue of A power k for any positive integer k. Eighth property. If lambda is an eigenvalue of the matrix A, then lambda is an eigenvalue of A transpose also. Ninth property. The product of eigenvalues counting multiplicity of a matrix equals the determinant of the matrix. Linearly independent eigenvectors. Theorem. Eigenvectors corresponding to distinct, that is different eigenvalues are linearly independent.